This is the second video for section 1.2, existence and uniqueness of solutions to initial value problems. So the question of existence and uniqueness, these are two questions in mathematics that are extremely important. The existence question asks, in this section, does a first order initial value problem have a solution? And the uniqueness question asks, if it has a solution, is this the only solution? And so we would say that such a solution is unique. We're only going to consider first order initial value problems in this section. Later on, we'll consider second order initial value problems and their existence and uniqueness of solutions. So let's consider an example. Let's look at the differential equation dy dx equals y to the 2/3 with initial condition y of 0 equals 0. And we'd like to know if this initial value problem has a unique solution. So you should check for yourself that y of x equals x over 3 quantity cubed is a solution. But maybe right away you can see that in fact there's another solution to this initial value problem, namely the function y of x being uniquely equal to 0, so the constant function, is also a solution. So what we would say in this case is that this initial value problem does not have a unique solution. Now, being mathematicians, we would like to know when we're given a differential equation, we would like some way to tell if it's going to have a solution, and if it has a solution, whether or not that solution is going to be unique. And it turns out we have such a tool. It is the existence and uniqueness to first order initial value problems theorem, which I'm not going to rewrite here. You can read it, Theorem 1.2.1. And you should pause this video, get out your book, and read that theorem. Seriously, do it. So this theorem that you just read gives you sufficient conditions for local existence and uniqueness. Sufficient means if these conditions are satisfied, I'm guaranteed to have existence and uniqueness of solutions. These conditions are not necessary, so it's possible I could have a differential equation that has a unique solution that does not satisfy these conditions, but if these conditions are satisfied, guaranteed existence and uniqueness. The local caveat means that I'm only guaranteed a unique solution in some small neighborhood of my initial condition. And we'll parse through that theorem in class because it's kind of technically written, but that's the rough idea. So if my differential equation satisfies the criteria in Theorem 1.2.1, then I'm guaranteed a solution that is locally unique. So let's go back to our example of dy dx equals y to the 2/3, y of 0 equals 0, and see what went wrong. So in the parlance of Theorem 1.2.1, my function f of xy is the function y to the 2/3. So the existence and uniqueness theorem tells us to look at whether that function is continuous, and it is. It's continuous everywhere. Perfectly nice function. However, the existence and uniqueness theorem also tells us to take a look at df dy, and when we do that, when we take the partial derivative of f with respect to y, we see that we get 2/3 y to the negative 1/3, which of course is not continuous at 0 because it's a divide by 0, so the function's not even defined there, much less continuous. So the existence and uniqueness theorem does not hold. We don't satisfy the criteria of that theorem, so we cannot be guaranteed a unique solution to the initial value problem. And in fact, we saw earlier that we don't have a unique solution to the initial value problem. However, if we look at the region where both f and df dy are continuous, say in the upper half plane or everywhere where y is positive, and again, and you could also say, look at the lower half plane, everywhere that f is, everywhere that y is strictly negative, then both f and dy are continuous. And so our criteria for the for the existence and uniqueness theorem are satisfied. So if we had an initial condition, like say y of 1 equals 2, that point lives somewhere up in the upper half plane, like up here, then we would definitely have local existence and uniqueness. So what the theorem would say is that in some small neighborhood, we would have a solution would exist and it would be unique. So it would be the only solution curve passing through the point 1, 2. In class, like I said, we will parse through the technicalities of the existence and uniqueness theorem, and we'll talk a bit more about what does it mean for a solution to be locally unique.